Hello, Math 7 students. This is Open Up Resources, Unit 1, Lesson 4, Scaled Relationships. We have talked the last couple of lessons about scaled copies and even scale factors. In each one of those lessons and in each one of those examples that we've gone over, we've always been able to measure the side lengths of something. But we're going to run into a challenge today. If we look at these polygons, we can see that we can't say exactly how long each of the sides are. And even the old strategies that we used in the past, like talking about the diagonals being one tall and one across or something like that, is not going to work here. This is too tall, but exactly how far across is it? We can guess and say maybe it's a half or a third or a fourth, but we can't be very precise. And so we won't even be able to measure the diagonals in the same way that we have before. And so this lesson is looking at different ways that we can look and measure to see if these are scaled copies. This first example says that we are starting with these polygons, and they are for sure scaled copies of each other. So, it says name two pairs of corresponding angles. That way we can review some old vocabulary. And as we name our two pairs of corresponding angles, I want you to start looking at what are the sizes of the angles. Do you notice any similarities? Do you notice any anything that's worth mentioning? So as we get started here, I can see angle D corresponds to angle H and to angle L. So I'll write that down. Angle D, angle H, and angle L all correspond. We can also say that angle A, angle E, and angle I all correspond. Notice that those angles are in the same position in each one of those figures. That's why we call them those corresponding angles. So again, angle A, angle E, and angle I. And so the next part says, what can you say about the sizes of these angles? Anything that you observe? It almost looks like they are the same measurement. This one is nice and big. It's an obtuse angle. That's a big obtuse angle. Big obtuse angle. So even though the figures are getting bigger or smaller in this case, it looks like that angle is staying the same. And this one is a smaller acute angle, smaller acute angle, smaller acute angle. So even though the figure size might change, it almost looks like those angles are staying the same. And that gets us into the next question. It says check your prediction by measuring at least one pair of corresponding angles using a protractor. So I'm going to write down that prediction. It looks like the angles are the same. Now let's actually measure. Now I am going to be measuring digitally using my digital protractor, and this is going to be a little bit more difficult than when we did it on paper with our actual protractor. So this isn't going to go completely smooth. I'm just going to do the best I can, and I'm asking that you guys do the best you can. If you've printed this out and you have your own protractor in front of you, you can also measure instead of just watching me do it. In fact, that's what I would encourage you to do, is to pause the video and to measure those angles. So I would be measuring DHL and A, E, and I, and we're going to measure those and compare them. As we measure, because our measurements are going to be a little bit off, especially mine since I'm going to be using this on the screen here, it says let's help us out and let's measure to the nearest 5 degrees. And what that means is if I end up measuring an angle that's 21 degrees, instead of trying to be precise and say 21 degrees, I would round that to the nearest 5th degree, which would be 20 degrees. Versus if I have something like 24 degrees, well, 24 degrees, that's going to round to 25 degrees, and so I would call it a 25-degree angle. So again, I know that we want to be precise, but sometimes we're limited by our tools, and so that's why we're going to be rounding a little bit here. So pause the video and measure your angles. I will also be measuring my angles when we return, but pause the video now to get your angles measured. Okay, we're back. Let's take a look at this. I am going to be measuring these angles so that you can see how it's done and so that we can get an idea of whether or not our prediction was accurate. So again, remember the strategy for measuring the angles. I need to line up the center part of the protractor at the vertex, and you can see that my bottom is not in alignment, so I've got to rotate it a little bit to get it there. That looks like it's where it needs to be. And so now I will measure that angle. And again, just like I mentioned on the video, because this protractor has that hole in the middle, it's a little bit difficult to see where it goes. And so I'm going to have to extend that line long enough and wide enough to see. Using this protractor, we counting starting at the 0, counting up 0, 10, 20, 30, all the way until we get up to, it looks like it's a 130-degree angle. So roughly 130 degrees. I'm going to move over to the next one and see if angle H looks to be the same. Trying to line up that vertex and line up that bottom line. And just like before, I'm still going to have to extend that line. And it looks like it is. It's also 130 degrees. My prediction is coming true so far. So this was angle D, 130 degrees, H, 130 degrees. Let's take a look at angle L. Getting that lined up. Need to go through and extend that line. And sure enough, 130 degrees. So yeah, I think so. I think that, I mean, at least that one was right. So maybe we're right all the time. Let's test out that red angle too, just to see if they really truly are the same. So, oops. This time, I'm going to spin this around, line it up there with the bottom, trying to line up that vertex. Uh-oh, I lost my rotation. All right, I think that that's probably as good as it's going to get. And it looks like I also am going to need to extend this line just a bit. My red angle, angle A, that looks like it is 50 degrees. A looks like it's 50 degrees. Let's take a look at the corresponding angles. Lining that up here. E, and that looks also like it's 50 degrees. I didn't have to extend the line that time. So angle E also appears to be 50 degrees. And let's check out our smallest figure. Surely the angle changed when it got to be a smaller figure. Let's extend that line and see what we can see. Huh, interesting. That looks like that's also 50 degrees. So they looked like they were the same, and indeed they are all that same angle measure. That's going to be important later on. So let's remember that as we move on in this lesson. 3 quadrilaterals. Now it says using the diagram above, so we're using that same diagram. We focused on the angles. Angles looked like they were the same, measured them, they were the same. Now we're going to start looking at distances. And again, the distances are a little bit more difficult to measure on this one, so we're going to look for distances that we can measure. It says we have quadrilateral ABCD. Let's look at the distance from D to B. So when I look at that distance from D to B, that means that I am now going through that figure. Instead of trying to measure an actual side length, I'm measuring something that is actually easy to measure. And I can see that that's 1, 2, 3, 4, which is why that is listed here in our table. And let's measure that same in each of these other figures, only it's not going to be DB. The corresponding would be HF, and that is 1, 2, 3, 4, 5, 6. So you can see that listed in the table here, 6, and that was, oh, I forgot already, FH? HF was also 6. And let's move on to that same one in IJKL. Again, I'm going to actually get rid of this guy now. Maybe. There we go. Now I can actually see that this is going to be LJ, and that's 2. So see how much easier that was? Instead of trying to figure out how long that was, we can go and measure pieces of that polygon that are easier, even though they're not the side length. So that was, again, LJ with a length of 2. Go ahead and fill that out for the side length, or not the side length, but for the distance that corresponds to AC. I'll highlight it in the first one, and I want you to fill that out for the rest. AC starts at the bottom and we measure up. And notice that it's not going through crosshairs. However, we can easily see that it starts down here and it ends up here. So we can still count up 1, 2, 3, 4, 5, 6. So AC had a length of 6. That's what's listed here. Measure that in the corresponding, or that same corresponding distance in the other two polygons and list them here in your table. Pause the video long enough to give you a chance to do that. All right, and these are the lengths that I measured out. I hope that they match what you have. The next question says, look at those values and what do you notice? What specifically, knowing that we are dealing with scaled copies, knowing that we've also had lessons on scale factor, can you find that scale factor? Can you see how they're changing from one to the next? Normally we've looked at side lengths as we've done this. Now we're looking at just distances and not specifically those side lengths. But I still hope you notice things like this, that the 4 can be multiplied by 1/2 to get 2. Half of 4 is 2, and we see that same thing here. 6 multiplied by 1/2 is 3. We can also see 4 multiplied by 1.5 is how we get 6. The same as 6 multiplied by 1.5 is how we get that 9. And if we wanted to even start comparing this relationship, a 6 multiplied by 1/3 is how I get 2. 9 multiplied by 1/3 is how I get the 3. And interestingly enough, we can also even go other directions, like the 2 multiplied by 2 is how I get the 4. And this 3 multiplied by 2 is how I get the 6. So hopefully you're seeing that same sort of concept of scaling up and scaling down, even though we're not dealing with the side lengths of a polygon. It says pause here so the teacher can review your work, but we just reviewed that together, so we're good. We're just going to continue on with the next example. It says the larger figure is a scaled copy of the smaller figure. And it says if AE is equal to 4. Now AE again is not actually drawn in the figure. It's this distance here. And it says AE is 4. But based on what we saw before, can you figure out what this corresponding distance is going to be? Can you figure out what that corresponding distance is going to be? And it might be tricky at first, but you can, because the information that it gives us is we know that this 6 scaled up to become a 15. So we have to do some work here. How does that 6 multiply? Because that's what we do with our scale factors, we multiply. How does that 6 multiply to give us 15? Now this might need some mental math, maybe some calculations, but if you stop and you think for a second, let's see, 6 times 2 is 12, so that's a little bit too small. 6 times 3 is 18, and that's a little bit too big, so it's probably going to be somewhere smack dab in the middle. 6 times 2.5 is going to be smack dab in the middle at 15. So our scale factor is 2.5 because we are multiplying by the number 2.5. So if this is 4, can we multiply by that same scale factor of 2.5 here, even though this distance isn't part of the figure? And the answer is yes. 4 times 2.5 is going to be equal to 10. So it says show or explain your reasoning. We showed our work here, but it's still probably worth mentioning. What we did is we used the existing information to find the scale factor. And once we use that existing information to find the scale factor, then we knew what the scale factor was, so we can use the scale factor to find the other pieces of information. Remembering that we multiply with our scale factor. Use scale factor to multiply and find new distances. All right, and now we're also going to work backwards. What if IK is equal to 5? Can you use that information to figure out what this distance would have been? So now we need to think about it again a little bit differently. We remember that when I'm scaling up, wrong color, when I'm scaling up, I'm going to be multiplying by 2.5. So that means I had some number, and I don't know what that number is, but I had some number, and I multiplied it by 2.5 because that's the scale factor, and after multiplying it by 2.5 I ended up with the distance of 5. So what is that number? Can you figure it out? Pause the video, do some quick mental calculations, see if you can figure that out. We'll come back together in just a second. All right, and hopefully you were able to calculate and figure out that the number would have been 2. 2 multiplied by 2.5 is equal to 5. And if you're struggling with that, that's okay. A quick review is what I would have done to calculate this is instead of leaving it just a big blank space, I would have turned it into a variable. X multiplied by 2.5 is equal to 5. And now you have an equation, and we can solve this equation because we understand that to undo multiplication, we simply need to divide. So I'm dividing each side by 2.5 to undo this multiplication, and whatever I do to one side, I make sure to do to the other side. And now I know that x is equal to, well, you do have calculators, so 5 divided by 2.5 is 2. So it doesn't all have to be mental math. You can use some old strategies that have worked in the past, like setting up and solving equations, and of course using your tools like your calculator. So here are some new copies, and the question is scaled or not scaled. My says that polygon ZSCH is a scaled polygon of XJYN, but Noah disagrees. What do you think? Do you agree with either of them? Explain or show your reasoning. I don't want to guide you through this problem because it's your opinion. What do you think? Do you agree with Mai, who says that it's a scaled copy, or do you agree with Noah, who says no, it's not? You form your own conclusions, but I do want to encourage you to observe everything that you see here. Think about what we just learned in our last two examples and see if you can apply that to form a conclusion right now. Do you agree with Mai or Noah? Quickly write down who you agree with. And then I want you to take the time to go through each of these steps. What it's asking you to do, and again, I'll have you pause the video so that you can do all of this, but I want you to do is measure XY and measure ZC. Then measure JN and measure SH. Once you have those measurements, find out, are they scaled copies? Can we scale up to get from one number to the next? Can we scale down to get from one number to the next? And I also want you to Part 3, it says measure at least 3 pairs of corresponding angles, just like we did in our first example. So you're going to fill out the table, compare those measurements, compare the lengths, but then I also want you to compare the angle measures. Pause the video long enough to get that done. All right, again, we're back from measuring all of those angles. I'm not going to walk you through the steps of measuring each of those angles. It's something that we practiced, and so I'm hoping that you're okay to do that, but do compare your answers against mine. XY, the distance is 6. ZC, the distance is 4. JN, the distance is 9, and SH, the distance is 6. And then all of those measurements, I went ahead and I wrote them all right here. Angle J and angle S, 40 degrees, so that same angle in each one of those figures have the same angle. And then angle Y and angle Z, when I compared those corresponding angles, that's angle Y and angle Z, they had measures of about 75 degrees. And again, it's okay if your measurements were a little bit off from mine, but the key thing is I want you to come to the same conclusion. Angle X and angle Z, that would be this angle here and this angle here, I did come up with different measurements. So again, your specific measurements might be a little bit different from mine, but I hope that you still agreed that X is different than Z. And N and H, I have these measurements. Again, even if yours are a little bit different from mine, the key thing is I hope that you measured accurately enough to see that N is different from H, even if your numbers are different from mine. So although when we observed in the table, we can see that if I wanted to go from 6 to 4, I would be multiplying by 2/3. Or if you looked at it in reverse order, you can see that 4 multiplied by 1.5 is 6, and 6 multiplied by 1.5 is 9. The distances appear to tell us that these are scaled copies, but we're also learning something else. When I look at these angle measurements, I can see I have some angles that are definitely not the same. Angles X and Z are definitely not the same, and N and H are definitely not the same. And according to our other examples, they should be the same if they're scaled copies. So do these results change the answer to the first question? Well, it depends. If you agreed with Mai, hopefully these results changed your opinion. If you agreed with Noah, hopefully you say no, I know that they are not scaled copies because the angles from one figure to the other are not the same. So are these scaled copies? And the answer is no. The angle measures here, right here, being different, tell us that these are not scaled copies. They might look like it in the beginning, and even looking at the distances, we might be fooled, but I want you to take away from this, we need to make sure that we're looking at the distances as well as our angle measures. Here we are on to our next example. We've got two more quadrilaterals, and here we can see we've got our distances, 2, 4, 4, 6, 1, 3, 3, 4, and we have our angles. So 60 degrees corresponds with 60 degrees, looks good so far. 120 with 120, 120 with 120, and 60 with 60, looks pretty good. Kiran says that polygon EFGH is a scaled copy of ABCD, but Lynn disagrees. So who do you agree with? Do you agree with Kiran, who says that they are scaled copies, or do you agree with Lynn? Pause the video long enough for you to collect all of the data that you need to form your own opinion. Are they scaled copies or not? And this time, you might have been fooled by the angles. All of the angles are the same, but remember there's two pieces of information we need to be looking at. Look at the angles, yes, but you also need to make sure that you're comparing those side lengths too. We saw before that side lengths or distances weren't enough, and now we're seeing the angles also are not enough. So we can see that a 1 changes to a 2 using a scale factor of 2. But when I try and use that same scale factor here, 3 times 2, I get a length of 4. That didn't work out. Same thing here, and same thing here. We're not getting the distances that we should be, so although the angles work, this time the distances do not. So I am going to say no. Lynn is correct. The distances use different scale factors, and they should be using the same scale factor. Okay. The Are You Ready for More? Again, it's a really great deep thinking question, but I am going to skip it for the sake of time. If you want to pause the video and give yourself some good opportunity to think about that, I think it would be a good exercise for you to do. Now we're ready for our cool down. At least if you printed the packet, it looks like we're to the cool down, but I actually want us to go through the lesson summary first. All right, and with this summary, here's the things that I want you to take away. Oops. Gotta love technology, always fighting against me. Here's the things that I want to take away from this. All distances in a scaled copy can be found by multiplying the corresponding distances in the original figure by the same scale factor, whether or not the endpoints are connected by the segment. So in looking at these two examples, the scale factor is 3 because I'm measuring from TX and BF. I'm not measuring the diagonals or anything like that. I said, hey, let's just measure BF and TX, and that's 2, and this is 6. 2 times 3 is 6, so that scale factor is 3. We can also observe that same thing here. BC is 2, and TU is also 6. So we can compare all of these things, and we don't always have to focus on those diagonals if they're too hard to measure. We also observed from this lesson that all angles in the copy have the same measure as the corresponding angles in the original figure. Just like we see in these triangles, 42 degrees corresponds with 42 degrees, 60 degrees with 60 degrees, 78 degrees with 78 degrees. It says these observations can help explain why one figure is not a scaled copy of another, just like we see here. Even though these two rectangles are both rectangles and they all have 90-degree angles in all of those corners, we also can compare the side lengths too. And we can see that sure, 1 times 2 is 2, but we lose that as soon as we start looking at some of these other sides. So grand takeaway is we need to make sure that we are comparing our angle measures as well as our distances or side lengths. Now let's go back to our cool down. Here are two polygons. Is PQRST a scaled copy of ABCDE? Anytime you want to pause the video and give yourself that think time instead of waiting for me to go over it is fantastic. But I want to point out that this distance here is 2 and this distance here is 4, so it looks like we would have a scale copy of 2. Or scale factor of 2, I'm sorry. 2 times 2 is 4. So with this distance of 1, I would expect to see a distance of 2, and I don't. So the answer is no, because we're using different scale factors. And according to our summary, we should be using the same scale factors. All right, that's it. Your homework is that lesson 4 practice problems. Make sure you get that done, and we'll see you next time.